Hello folks, in this video we're going to talk about units. What are the basic units of measurement that we use when we go into the lab? So we'll start with a careful look at the basic measurements that we make when we go into the lab, the simple measurements that we make in the lab, and how we define those measurements and then use those measurements to do various calculations. We'll of course be focusing on the metric system as we go through this, and in fact specifically define what's known as the International System of Units and the standards used to determine that international system. All right, so what are the standard measurements? We'll start with mass. And of course, you probably know mass, and you associate mass, of course, with weight, but mass and weight are not the same thing, and this is something that we'll talk about a little bit later on. Mass is related to weight, but weight itself is a force that depends on the gravitational attraction to a particular body. So mass you can think of more or less as the amount of stuff that makes up matter. There's, of course, a more rigorous definition of mass, and of course how that comes about is something that has been studied, and a theory has been developed associated with something called the Higgs boson, and that's beyond the scope of what we're talking about here, but you may have heard about that. So mass is kind of like the amount of stuff that we have, and we'll be looking again at how that relates to various forces associated with different types of processes. And then, of course, distance is something that we measure. You know, distance when we talk about, there's a distance of 1 meter between one point in space and another point in space. So distance is something that is related to spatial difference in locations. We'll talk about time, of course. Time is a crucial element that we measure when trying to determine various properties in the lab. Charge. We talk about electrical charge, positive and negative charges, and so that is also something that's crucial that we understand the basic definitions and the units used to determine charge. Temperature, of course, and we'll talk about the various units of temperature, but the ones that we use most crucially in our calculations. And then, of course, we need to be learning about the various prefixes that are associated with each of these. So that these are things that you'll typically see. There are a lot of prefixes associated with these things. So nano is a prefix that we use when we're talking about 1/billionth of a substance, a particular measurement, and 1/billionth corresponds to 10 to the minus 9. Of that. So when we talk about nanometers, which we'll talk about in a little bit, that's 1/billionth of a meter, 10 to the minus 9 meters. Another one that we'll use frequently is micro, which is 10 to the minus 6, or 1/millionth of a substance. Milli is 1/1000th, 10 to the minus 3. And then moving to the other side of things, kilo corresponds to 1,000, or 10 to the third. Mega corresponds to 1,000,000, or 10 to the sixth. And finally, giga is 1,000,000,000, and that's 10 to the 9th. So these are all important prefixes that will be attached to the basic units we're going to use. So it's important that you know what the meanings of these prefixes are when we talk about various kinds of measurements and various kinds of properties. Okay, so let's start with mass. Now again, frequently people associate mass with weight, and again, they're not the same thing. So when we talk about pounds, for example, in our English system, that is not a mass. That is a weight. Okay? And weight depends on gravity, the gravitational attraction. Okay? So your weight here on Earth is different than it would be on the moon because the gravitational attraction, because the moon's much smaller than the Earth, the gravitational attraction on the moon is roughly 1/6 of that of Earth. So your weight is roughly 1/6 of your weight here on Earth. So pounds is not something that we use when we're talking about mass. Your mass is the same everywhere. So while pounds or weight will depend on gravitational attraction to a particular body, your mass is always the same. Your mass here on Earth is the same as your mass on the moon. So when we talk about mass, typically in the metric system, you've certainly we've talked about grams, and that's something that you're probably familiar with when we talk about that. And of course, if we were talking about kilograms, as we learned from our prefixes, that would be 1,000 grams. So as we'll learn, kilograms actually is something we're going to be using more frequently than grams, just because of our international system of units, which we'll talk about in a few minutes. But when we talk about grams, we are talking about mass. Okay, and in the laboratory, we measure mass by using something that's typically called a balance. A mechanical balance was something that compared the mass of a substance to a standard. These days we use electronic balances in the lab, where we place our particular substance on a platform of some kind, and the electronics within the balance itself determine the mass. So that's what we're talking about. Grams is typically, and kilograms are typically units that we're going to be using when looking at mass. Okay, and again, I can't emphasize this enough. Mass and weight are different things. So understand that distinction. All right, so when we talk about distance, the distance between two different points in space. Again, in the metric system, we're going to use meters. Okay, and I'm going to look at conversion factors here in a few minutes, using Wolfram Alpha to show you conversion between those. So when we talk about meters, of course, and typically, for example, in track and field these days, in the international events that we're talking about, for example, the 100-meter dash. Or a 1,500-meter run, and that's distinct from, going back to my day, because I'm really old. When I was in high school, the track and field events, you had the 100-yard dash. We don't have that anymore. It's now the 100-meter dash. A meter and a yard are close to the same, not quite the same. And again, I'm going to show you how to use Wolfram Alpha in a couple of minutes to make these conversions. So that's meters. And of course, if we want to talk about, for example, a lot of times when we're making measurements in the lab, for example, we'll be looking at something called millimeters, which is abbreviated mm, and that's 1/1000th of a meter. When we start looking at things on the order of atomic sizes, for example, we might be talking about nanometers. Of course, you've heard the term nanotechnology, and that comes from the fact that the nanotechnology is associated with very small things. So a nanometer is 10 to the minus 9 meters. And just to kind of put things in perspective, the typical size of an atom is on the order of a few tenths of a nanometer. The hydrogen atom, for example, has a size of roughly 10 to the minus 10 meters, okay, which corresponds to 0.1 nanometers. Okay, so when we talk about nanotechnology and things like that, we're talking about things that are really, really, really quite small. So I'm seeing that I've got some issues here with what's appearing on the screen, so I'm just going to pause for a few seconds and see if I can fix this. Okay, so I am back, and hopefully we got the screen fixed so it won't change again. So anyway, when we talk about meters, we can see that nanometers is something, when we talk about atoms and molecules and such, that's going to be something that we're going to be looking at. Also, when it comes to light and wavelengths of light, we're going to be talking frequently in terms of nanometers as well. Okay, and then of course there's time, which we mentioned, and again we can talk about time in terms of seconds. And of course, again, applying the various prefixes, excuse me, a nanosecond, NS, is 10 to the minus 9 seconds, okay? And so when we talk about these kinds of things and talk about nanoseconds, we're talking about processes that, we can talk about processes that happen really, really fast. For example, in my research lab, we actually do work where we're studying molecular events that are occurring on a nanosecond time scale, 10 to the minus 9 seconds. Just to give you some perspective, we haven't talked about the prefix pico. Pico is 10 to the minus 12, and femto, and these are not prefixes we're going to be using very often, is 10 to the minus 15. But the kinds of events that occur on a molecular scale can be really, really fast. So for example, we talk about just the process of vision, the kind of reaction that's going on in your eye, actually. So there is a biochemical reaction that's going on in your eye that is leading to the perception of vision. And those processes are happening on the order of a few hundred femtoseconds, say 10 to the minus 13 seconds. So there are a lot of things that are going on really, really fast when you get down to the small size of atoms, and they're moving at very high speeds. And what's going on internally in atoms is happening at very high rates and very small time scales. But these are the kinds of things we can actually, believe it or not, we can actually measure this stuff. This is stuff that we can measure in the lab using very sophisticated techniques, frequently involving lasers of some sort or another. So that would be seconds when we talk about that we use for time. When we talk about charge, there is the unit that we use is something called coulombs, all right? And just to give you some perspective on that, when we talk about, that atoms are made of electrons and a nucleus which has protons and neutrons, you're probably aware of this. The charge of an electron is roughly, you're probably already aware that electrons are negatively charged, so is roughly negative 1.6 times 10 to the minus 19 coulombs. So the coulomb itself, an electron has a very, very small charge. When we talk about electrical currents, for example, you've probably heard the term ampere or amp. An amp, 1 amp is defined as a current, and that's essentially the rate at which charge flows through an electrical circuit, of 1 coulomb per second. All right, so again, when you hear that term amp or ampere, that's just the rate at which charge flows through an electrical circuit, and 1 amp is 1 coulomb per second. Okay, so we're back, and we are talking about the temperature scale that we're going to be using, which is the absolute temperature scale, referred to as kelvins, represented by the symbol K. All right, and we don't say degrees Kelvin, we say kelvins. It's like degrees Celsius and degrees Fahrenheit. It is just kelvins. This is the absolute scale, meaning that 0 Kelvin is absolute zero, the lowest possible temperature. which in fact cannot be achieved experimentally. The laws of thermodynamics tell us we can never reach 0 kelvins. We get pretty darn close. In fact, there have been experiments where we have gotten down into the nanokelvin range. Which, if you'll recall, is 10 to the minus 9, 1/1000th of a Kelvin degree. But that's as low as we have been able to get. All right, so that's the Kelvin scale that we'll be using, and that compares to other scales of degrees Celsius and, of course, degree Fahrenheit. But again, the Kelvin scale is going to be the temperature scale that we're using in our calculations associated with thermodynamic properties. But just as a matter of relative conversion factors, the degrees Celsius, so for example, 0 degrees Celsius is equal to 273.15 kelvins. And so if you remember, 0 degrees Celsius, of course, is the freezing point of water at normal atmospheric pressures. And that corresponds to 273.15 kelvins. Now, when we talk about degrees Fahrenheit, of course, we know that the freezing point is 32 degrees Fahrenheit. And that, of course, also is corresponding to 273.15 kelvins. Boiling points, as you'll recall, for water at 1 atmosphere pressure is 100 degrees Celsius, which of course is equal to 373.15 kelvins, all right? And of course we know that for water in Fahrenheit is 212 degrees Fahrenheit corresponds to the boiling point. Now, the conversion between degrees Celsius and degrees Fahrenheit was if you took 9/5 times the degree Celsius temperature and add 32, that's going to give you the temperature in degrees Fahrenheit. So again, you can see that if it's 0 degrees Celsius, all right, that the freezing point's 32 degrees, and you can go ahead and do that conversion. Conversely, if you want to convert from degrees Fahrenheit to degrees Celsius, then you take the degrees Fahrenheit and you subtract 32, and then you multiply it by 5/9 would be the conversion factor for that. And as I've mentioned several times, in looking at conversion factors and things of that nature, we're going to look at Wolfram alpha in a little bit and learn how we can use Wolfram alpha for those conversion factors. So again, so the kelvins is going to be our absolute scale. That's the temperature scale that we're going to use in most of the calculations when we're dealing with thermodynamic and scientific properties of systems. All right, so there is an international system of units, and you could probably guess based on what I've really focused on in this particular discussion, and that is that sometimes it's called the MKS system, which is meters, kilograms, and seconds. So when we talk about international system of units, we're going to be using kilograms, meters, and seconds for our standard units system. So the other units that we're going to be talking about are going to be based on this. Just to give you an example, for example, energy, and we'll talk more about energy later on, the specifics of energy and the physics of energy and what energy, how energy is defined. But basically at this point, the standard unit of energy is the joule, represented by the symbol J. and that is related. So that's not a unit upon itself. Everything's based on this MKS system. So a joule is in this complicated fashion. You'll see why when we start looking at basic equations for this stuff. Okay, so we got a lot of background noise here with the dog barking next door, and people are mowing in the neighborhood today. It's a nice day. But the joule is equal to, in terms of our MKS system, meters, kilograms, seconds, is a kilogram over a meter squared, second squared. That's the basic definition of the joule. So again, everything is going to be based on this international system of units. All right, so what are the standards? I mean, so we've got these kilograms and meters and seconds and things, but there has to be a standard. I mean, there has to be, if we've got this international system, we just can't let everybody decide what a meter is or what a kilogram is. And there is a basic standard accepted internationally that's a definition of these units. And you can find it's actually, in recent years, it's actually changed a little bit to make it more precise. These definitions more precise, mostly based on atomic scale phenomena or the speed of light for the determination. For example, the kilogram, which used to be based on a solid object that was stored away in France as the object that corresponded to a kilogram, and every other definition of kilogram is relative to that. Well, that's changed because these objects do change over years. No matter how careful you are, you will lose a little bit of mass on these objects that are, no matter how safely they're saved over time. And so we're now basing this on measurements that can be done very precisely, and the kilogram is based on Planck's constant, and it's very precise measurement. Planck's constant, which is represented by H, is an atomic scale constant that's really, really important when dealing with atomic and molecular phenomena. Just, give you some perspective. It's 6.26626, and actually it has more precision than that, but I'm rounding it off, times 10 to the minus 34 joule second. So it's bizarre. Constant, but the actual definition of the kilogram now is relative to that constant, which can be very precisely measured. So the time period of a second is defined in terms of a transition between energy levels. We're going to learn, of course, that molecules, atoms, particles have levels of energy associated with them. And there is, when we talk about the difference in energy between those levels, we can use that to define periods of time. And I won't go into the details here. It's based on the hyperfine structure of the cesium atom, which is very rigorously and precisely defined. And so it is based on the difference between these energy levels. So again, the point is that these things are very precisely defined based on atomic properties. And interactions, for example, with light. Planck's constant, this transition between energy levels defining the second. The definition of the meter is in terms of the speed of light. Which is 2.998, and again I've rounded off here, 2.998 times 10 to the 8th meters per second. Again, the speed of light is very precisely defined, and the meter is defined in terms of that. So in essentially a meter is going to be how far light travels. If it travels 2.998 times 10 to the 8th meters per second, if I take the reciprocal of that, all right, it's how far light travels in that period. So for example, the definition of a meter is going to be 1 over 2.998 times 10 to the 8th meters per second. That is, again, defining the distance. Meter is defined in terms of the speed of light, and that's the point. It's defined in terms of the speed of light. So just to be clear, when we take the reciprocal of the speed of light, 1 over 2.998 times 10 to the 8th meters per second, we get 3.336 times 10 to the minus 9 seconds per meter. So the meter is defined as the distance light travels in 3.336 times 10 to the minus 9 seconds, or 3.336 nanoseconds. I hope that's clear. Going on to some of the other things that standards that we've talked about, the Coulomb that is defined as the charge of a proton. In terms of the charge of the proton, so that the charge of a proton, again, is roughly, and again, I'm rounding off here, but the charge of the proton is very small relative to the coulombs, but that's how it's defined. The coulomb's defined in terms of that charge of the proton, which is 1.602 times 10 to the minus 19 coulombs, and again, I'm rounding off here. And then Kelvin scale is defined relative to the triple point of, or actually the triple point of water is defined relative to the Kelvin scale. The Kelvin scale, obviously 0 kelvins is absolute 0, and that's an absolute. But the triple point of water is defined now in terms of that. And exactly what the triple point of water is, it's essentially a point at which the water vapor, solid water ice, and water liquid all exist at the same time. And so the magnitude of the Kelvin degrees is defined in such a way that it's 273.16 kelvins. So that is how these standards are defined. All right, so that's basically a glimpse of basic units that we're going to be using. We're going to be building on these units as we go through and do different kinds of calculations and different kinds of measurements. But these are the units that are going to be most important for the kinds of things that we're going to be using, and establish the standards that we're going to be using as we move through discussions of physics and chemistry and physical science in general. So in another video, we'll start working on how to use these units to do various computations. So in the meantime, if you have any questions, let me know. Hey folks, I know I promised that I would show you how to use Wolfram Alpha to do some unit manipulation, but this video is already too long, and I think you'll clearly agree with that. In fact, I've changed my clothes, right? I'm now powered by caffeine. You can't see the molecular structure, but let me just scroll down. There's the molecular structure of caffeine. So as a result, what I'm going to do is we're just going to take a break here, and I'm going to create another video, a separate video that will go through some manipulations in Wolfram Alpha and unit conversion, talk about a few other things. So you take a break too, relax a little bit, and be ready for the next one. I'll see you later.